Hello, dear viewers. Today, I want us to discuss a topic of what should be the extra dead load in slabs for residential building. So, I'm talking about the extra dead load in slabs, which you should input in your software. For example, if you're using any other software, any design software that you're using, what should be the extra dead load of residential build? Because most of the building that you will design for are residential, and inputting the incorrect load values would mean that you have not designed for the correct load value, and the structure may fail. Uh, so to avoid this, you have to make sure that you know the exact or the correct value that you should use for extra dead load. For self weight, most of the time is calculated automatically. But what about the extra dead load on slab? What should be the value? Because most of people, including me, I've been telling people to use one, a value of one, but I think this is not correct. Let's compare using this software here. Protostructure. Protostructure suggests that for rooms, if I select all of this, maybe holding shift, right click properties. Protostructure suggests that if I change here, that for rooms, that is rooms for that is residential, the value is about 2.375. Now that is protostructure suggestion. So let's just use that value instead of one, which I did in my previous video when I was comparing ETAB software and protostructure software. So let me go to the second floor. Do the same thing. Properties, additional, that is extra dead load, additional dead load for residential building. That is for room. Let's just use that value of 2.35 and let's design and see, because I know this is a particular building is a building for affordable housing, a project for government here in Kenya, which we did, and I know uh, what we should get for columns in terms of reinforcement and sizing. So we will use this, and we will use the values that we actually did on site to know if we actually collect. And I also use another reference for manual calculation from another engineer. Is called this engineer Mwangi Minor, and I'm having this spreadsheet, this particular here um, in my desktop, reference from engineer Gitua. So we'll also use the references from engineer Gitua, who has done a lot of building. And so this is this particular spreadsheet. So the value he used a partition load of 1.5 and finishes of 1.2. And you see apart from self weight of slab, there is an extra load of about 2.7. So this is residential building. Product structure suggests a value of 2.35. So let's use for rooms. Okay, and then close and up to the fourth floor. Property. Uh, Rooms. And then for the last floor, which is my fifth floor, I will use a value of properties. We can change it to, is it flat roof? Let's use flat roof. So for flat roof, it's just one. And then we can do the analysis. So let me go to 3D view. Let's do the analysis here in data structure building analysis. Okay, so this one also I've done the same thing. Let me unlock this model. Display load assign shell. I've done the same thing. Apply. You can see I have a shell of about 2.5. That is the extra dead load apart from slab. And I have a live load of about 2. No problem for rooms. I have other display load assign frame are dead. That is wall. Apply. You can see my wall load. I have a wall load of about 9.6 for rooms, and for parapet I have 3. Also here in product structure is the same thing. For this, because this building is actually done, so we know what we should get, and we have the architectural and the structural plans here. So if I go to number 46, this is actually what we should get in our columns. Let me expand this one. For the most critical columns, that is for staircase, we need to use 60-20 in the first and the foundation level up to the second floor. So building analysis, let's do building analysis, analyze. I already did the settings, so we need to know what we will get for our columns here. So here I'll also analyze, run analysis. So my suggestion is for residential building, don't use a value less than 2.5 for extra dead load. When you are using any software, don't use a value of less than 2.45 extra dead load on slab, just minimum 2.5. That should be the value. Because even though Protastructure is suggesting a value of 2.35, let's use a value of 2.5, because as you can see from this engineer, he has partition of 1.5, finishes of 1.2. So this is 2.7. So the average, let's say 2.5. The average of 2.7 and 2.375. So just 2.5. And see if you're going to get, this is what we will get. Sorry for that. I'm cold, but please bear with me. Okay. You can go to post. Can see the beam reinforcement design. We don't need to worry about beams. Let me check the columns. We select all design. But I think because ETABS is the most advanced software, we will use the value for ETABS. If T16 passes, then that value is correct. From Protastructure T16, 6 T16, that is 4 corner bars T16 and 2 intermediate is passing. Let's see in here in CSI ETABS 2016. Let's run the concrete design and checks. Okay, this building has is having walls, that is machine cut masonry wall. So I think the building is not sway structure because it is braced. Because As long as there are those walls, there are those walls, it means that the building is braced. So when you're designing the columns in CSR ETABS, it will not be sway structure, it will be just non-sway. Right? So let's see. Let me click this column, and for example, overwrite. I think it is sway. Okay, we will change that to non-sway. But first, let's see the failed members. No, I don't think so because some members are overstressed. This is the problem with this version of ETA because as long as this is failing in capacity is OS, it's overstressed. So let's go to design. I mean design concrete frame. Um, view and preferences. Okay. So we need to check these columns. So let me go back to define. Let's unlock the model. We need to know which define. Go to properties. We need to go to property frames. I need to know the types of columns I have. So modify. Have these columns. That is T16, 4 corner bars and 2 intermediate, T16 and T8 at 200, as we have used in this affordable T8 at 200 links. This is probably by government of Kenya. So we are going to use it as our reference. We're going to use a suggestion from Structure as our reference, and this manual design from an engineer, another engineer as our reference. So okay, we have that type of column. I have this type of column. It's just the orientation has changed, but it is more or less the same things uh, in terms of rebus size. And I have this another column here. Now this one, let me change this one to T20. So we need 40-20 and 40-20 corner bars, right? So then 2T20 intermediate. Okay. So this column, so let's run the analysis and then run the design. We see if the columns are still going to be overstressed. If they are overstressed, we change them to non-sway because obviously these columns are not sway, they are non-sway. Because as long as they are braced, they are not sway. So let's run the design, complete design. So I know these columns are non-sway because I was there in construction. As you can see here in this drawing, the rendered view from the rendered view for these, you can see we have masonry walls. So these obviously they are braced, so they are not sway. I'll go back to page 46. Obviously, we have seen for the most critical columns, we were using 60-20s. So there's no need to, but we just confirm up from the foundation level, the ground floor level, and the first floor, we use 60-20. And there is also these columns which were passing at 60-16 from the foundation level. But the size is obviously 400 by 200, 400 by 200, as I've modeled in both Rota and ETAB. You can see 400 by 200, right? Now these columns are overstressed, right? So let me overwrite. So this column is new, the column with 40 T20s. So let me overwrite, and let's say it's a non-sway. It is still overstressed. Okay. overstressed, even those all reds, just select them, override, frame time, none sway. Okay. So for all those overstressed column, I'll select them. So this column is not overstressed. Let me see. This is not overstressed. This column here is not overstressed, but that column is overstressed, and this one is also overstressed. So override non-sway. All columns are non-sway. Override non-sway. Override non-sway. So change the non-sway moment 0.7. 0.7. Still it is overstressed. Then so I'll select all these columns and that. Then I will unlock the model, assign section properties. I'll assign that. That is new. So I can just select this, right click, show selected objects only. And then from here, escape, select object types, column, right click, okay. Then run the analysis. Run the design. If that fails, we are going to change the grade of steel, because obviously I know from the site we used grade 500 of steel, but here the default value in ETABS is not grade 500. So I'm sure that could also lead to that overstressed warning. Okay, now how many are remaining? These two are passed. This one is still overstressed. This one is still overstressed. Okay. Um, go to settings, rebar. Okay. Let's go to analysis. Um, building analysis. So here we're using grade 500. You can see reinforcement, steel grade, edit material. So we can copy these values, this value of steel grade. Okay, we can copy them to ETABS. So I will unlock this model. Then I'll go to define. I'll define materials. I'll define rebar, modify show properties. Okay. Now instead I will use these values. Modulus of elasticity is 200,000. Shear modulus is 79,434. Modulus of elasticity is 200,000. Okay, 200,000. Coefficient of thermal expansion thermal effect is 0.000. Can we copy this value? Copy. Paste that value and just move that. Weight per unit volume. Weight per unit volume is that that is shear modulus Newton per millimeter squared. Let's see. Material tensile strength. Let's see a few. Tensile strength, Newton per millimeter. This one is in MPa. That is Fy. So this one, can I change this one to 500? Because I think MPa, convert MPa to this value. MPa to Newton per millimeter squared. Let's change the value. MPa to Newton per millimeter squared. So 1 megapascal is equals to 1 Newton per millimeter squared. If you check on your Google, can just check it on Google. So it means that this value here is this value here. Okay. Okay. So this one can also change to about expected yield strength. Should be a bit more, maybe 520. And then okay. Then advanced data. Do you need this bearing? Okay. Material dumping ratio. Do you have that? No. Okay. Okay. That is what I used. Let's now redo analysis. So that is the material we used in this affordable housing project. Now all members are not overstressed, but we need 60-20. This is evidence enough that this proves that the extra dead load on slabs should be a value of 2, because that is what these particular engineers used. We will change this value to 460 for columns, then analyze that. So I'm going to go with the value for item. So I think every time you are designing, don't under design, don't underload your slab. The value should be not less than 2.5 extra dead load on slab. Thanks for watching. See you in my next video.